Hello, I'm Bo from Sweden. Welcome to my series about DCC and electronics. This is the fourth video, E4, in this series. This episode is a direct follow-up from the E3 video. Today we will look into details around controlling solenoid turnouts. We won't waste any time, so let's start. In the last video, E3, I presented an overview of controlling solenoid turnout using RX480E, a 4-channel 433 MHz remote controller, and ESP32 with a CD4013BE flip-flop. The output from the CD4013BE is connected to the TB66 F&G H-bridge, that controlling either a 2 or 3 wire solenoid turnouts. Here you can see the components that been used. Here's the schematic for the turnout controller presented in the E3 video. Handle both 3 wires dual coil and 2 wires single coil turnouts. Using 2 types of motor drivers, the L293D or SN754410, both pin compatible, and the more effective TB6612 F&G. Let's look into each section of the schematic. Here you can see the power section. The input power is dependable on what type of motor driver that's used and what kind of turnouts that's going to be controlled. The TSR2 2450N is a high-performance switching regulator that can have 6.5 to 36 volts input and 5 volt 2 amp output. For this turnout controller board, the input should be around 12 to 16 volt. The capacitors handle fluctuations and keep the signals clean from noise. To know the input power that's needed, calculate 12 volt plus the power drop on the motor driver and what power the turnouts need to switch. Normally that is around 12 volt. The 5 volt will power the RX480E, the ESP32 or Arduino, and the motor drivers. If an ESP32 is used, then power the CD4013BE with the 3.3 volt from the ESP32. Otherwise, use the 5 volt from the Arduino. Here's the logic part of the schematic. Schottky diodes is protecting both the RX480E and the microcontroller's output. Pull-down resistors keep the signal to the CD4013BE low until the button is pressed, or it getting a high signal from the microcontroller. 0.1 microfarad decoupling capacitors on the VCC keep the signal clean. The logic by the CD4013BE is when it receives a signal on the clock input, the output is high on the Q1 and low on the non-Q. Next time there is an input signal on the clock, it will reverse polarity and Q1 will be low and the non-Q will be high. It switches polarity for each input signal on the clock pin. The output from the CD4013BE goes to a 22 microfarad capacitor marked C10 to C13 that will be discharged by the 10K pull-down resistors R9 to R12, resulting in a 250 milliseconds pulse to the microcontroller that handle the turnouts. A big 1000 microfarad capacitor Mark C1 is working as a backup battery on the VM Plus that's feeding the power to the turnouts. Of course, we could use a smaller capacitor like 470 microfarad if a less power-hungry turnout is used. Both the 5V and the VM Plus have 0.1 microfarad decoupling capacitors. If a 2-wire turnout is used, skip the VM Plus connection that's used for the common connection on the 3-wire turnout, and only use the 1, 3, 4 and 6 outputs. The TB66F and G is protected by diodes D9 to D12 when the capacitor is charging up. You can safely use the TB6612F and G for both power-hungry dual-coil turnouts and 2-wire single-coil bipolar turnouts. Here's an alternative. If we're going to control less power-hungry turnouts, like single-coil or new, modern 3-wire turnouts that only need about 0.5 amp or less, you could use the L293D or SM754410 H-bridge motor drivers. Both is a 16-pin DIP, pin-compatible, and the L293D have built-in protective diodes. The SM754410 doesn't, so if you're using that, protected diodes is recommended. Both is having a high voltage drop, about 2.5 to 3 volt, generating heat of course, and only accept 5 volt logic. The L293D handles 600 mA and can have a peak up to 1.2 amp. The 754410 can handle 1 amp and have a peak up to 2 amp. The more modern TB6612F and G can handle 1.2 amp and peak up to 3.2 amp. But the voltage should be about 2.5 to 13.5 volt and absolutely a maximum of 15 volt. It has a low voltage drop, low heat, and accept 2.7 to 5.5 volt logic. It's only available in SND format or as a module for pin connection. It's also recommended to use protective diodes since it doesn't have anything built in. It's very easy to add a microcontroller like the ESP32 or Arduino. Only 4 outputs pin is needed. Normally you will use 2 output pins for each turnout. Then you can control the turnouts from both the remote 433 MHz controller and from DCC commands by the microcontroller. Using WICS No Rail, make the connection to the controller wireless. WICS is also giving you ready-to-mount PCBs and make one-click installation of both the WICS and the No Rail C++ code. You will find a link to the schematic in the description.
That's all for this video. If you're interested, there are and will be more videos divided into 2 series and playlists. In the DCC Electronics series, you get a nice overview of the technology and new solutions. In the WICS Wireless Control System series, you can learn about this add-on in the Now Rail system, making it user-friendly, simplify use and installation. The previous Newbies Journey series is moving to a Swedish Channel, Colorado in N scale. And if you subscribe, you will have a notification when the videos are released. Also, you will be supporting the channel. Thank you for watching this video. Hope you enjoyed it. We look forward to sharing our next video with you. Until next time, take care and happy railroading.